So let us start. Our topic of discussion today is Doppler effect. So something important that you should know before starting with the topic is the formula that we are going to use. Now this formula is important. You'll use it in most of your calculation questions. Now that formula is if L is equal to V plus or minus VL all over V plus or minus Vs times Fs. Now, what do each of those components represent? Our FL represents the frequency of the listener. Frequency is measured in hertz. The symbol for hertz is Hz. All the L's represent listeners. All the S's represent sources. So FL is the frequency of the listener. Fs is the frequency of the source. The source is where the sound is originating from. For example, if there's an ambulance in the distance that's making a noise from its siren, that is going to be the source, and because you are listening to that ambulance, you are now going to be the listener. Our V represents 340 meters per second. In most cases, they usually give it to you. Our VL represents the velocity of the listener, and our Vs represents the velocity of the source. Okay. Now, that plus or minus is the confusing part, right? So how do we know whether we're supposed to have a plus on top or a minus on top, or a plus at the bottom or a minus at the bottom? So how we identify our signs is based on whether the object is moving towards the source or towards the listener or away from it. So if we have a source that is moving, or rather, let's state that our source is stationary, okay? Now, if we are moving towards that source, we'll use a plus on top and a minus at the bottom. If we are moving away, we will use a minus on top and a plus at the bottom. So let us make a note of that. If it is towards, our formula is now going to be FL equals V plus VL all over V minus Vs times Fs. Now, keep in mind, if it's moving towards, plus on top, minus at the bottom. If it is moving away, it then becomes FL equals V minus VL all over V plus Vs times Vfs. So moving towards, plus. Moving away, it's minus. That is extremely important. In a lot of the cases in your exam paper questions, you'll find a question that requires you to use simultaneous equations, whereby you are expected to create an equation for an object moving away and an object moving towards. So how do you look at something like that? So keep in mind, if we have an object, let's state this is our object, okay? Now, if we are passing this object, let's say from left to right, we are passing that object. As we move towards the object, we are moving towards, therefore plus on top, minus at the bottom. Once we pass that particular object, we are then moving away from the object. So minus on top, plus at the bottom. So if something is moving past an object, or put yourself in that position. If you are moving past an object, as you're moving towards that object, the sound will get louder and louder and louder as you get closer and closer and closer to that object. Once you pass that particular object and start to move away, sound will get softer and softer as you move a greater distance away. So when you move towards the object, the sound is louder. When you move away from the object, the sound is softer, okay, or lower. So that is how you can now use simultaneous equations to incorporate both the towards and away in order to calculate for a specified value. Okay, so we'll have a look at that when we do a few past paper questions. So this is your main formula that you should understand, you should be able to use, and hopefully you should be fine if you know how to use this. Okay, so let's have a look. Our first question is from a November 2017 exam paper. I believe I have 4 questions up today. Hopefully we do get a chance to go through all 4. Whatever we don't cover, I'll post it in the group and you can do it as homework, okay? So I've put up 2017, 2018, 2020, and 2021 for today. So we've got a question from 2017, question 6. A police car moving at a constant velocity with its siren on. So because this police car has its siren turned on, that means that there is a noise that is being emitted from that siren. So therefore, our police car is going to be considered our source, because the noise is originating from that police car. So it states question 6. A police car moving at a constant velocity with its siren on passes a stationary listener. So the listener is stationary, meaning that it has a velocity of 0. Therefore, VL will be 0 meters per second. The graph below shows the changes in the frequency of the sound of the siren detected by the listener. So this graph represents the frequencies detected by the listener. Okay, so keep that in mind. This graph is for the listener, not the source, which means that this graph represents the, who is it? Okay, so it's just a stationary listener. They didn't specify who this is. So it can be some random guy standing on the street. Okay, so if this is our street, we've got some random guy standing over here. Now, this guy is stationary. Maybe he's playing with his phone or he's just standing there and doing whatever. Now, as this guy is standing there, we've got this police car that's moving past the guy. Okay, so this car is now moving past this guy. So keep in mind what I mentioned earlier. If you're going to move past someone, so as the police car is getting closer to the guy, he's moving towards him. And when the police car passes him and moves away, this guy is going to hear a lower frequency. So the sound will be softer. So as you can see, within this one motion of just to move straight past someone or to drive straight past someone, there's 2 situations taking place. Situation number 1, you're moving towards that person. Therefore, the sound emitted from your vehicle is going to be louder. Then scenario number 2, once you've passed that person and you start to move away from them, the sound emitted from your vehicle is then going to be softer. Okay, so that is what you need to understand from this. So within this one motion of just moving or of just driving straight past someone, there's 2 different situations that take place, and due to that we will have 2 different frequencies that arise. So as you can see from the graph, we've got time. So always remember, at time 0, that is when the graph starts, or where the situation or the scenario that's taking place, that's when it starts at time 0. So if we look at our graph, at time 0, we have a frequency of 170 hertz. Then as time progresses, as time moves on, you can see that this frequency drops to 130 hertz. So why is that? The reason behind that is what we've just explained. So the car, or the police car more specifically, was moving towards the listener. Because it was moving towards the listener, it had a greater frequency. So the frequency of the listener was 170 hertz. That is when the police car was moving towards the listener. Then you can see at this point that it changes. I'm going to highlight it. At this point whereby the frequency changes, that is the point whereby the police car passes this individual. So that is this point here whereby the police car passes. Once the police car passes this individual, it then starts to move away from this person. So because it's moving away from the person, the frequency detected by the listener or by that person is then lower. So it's then going to be 130 hertz. Okay, so we've got our frequency as the object, or rather as the police car moves towards our listener, which is 170 hertz. We've got the frequency of the listener as this police car moves away from the listener, which is 130 hertz. That yellow line that I've highlighted indicates the change whereby this police car is moving towards then away. So that is the change whereby it passes, okay? Now we've got our first question, question 6.1, state the Doppler effect in words. So you can find that definition in your textbook. I'll mostly focus on the calculation questions for today. Now we've got question 6.2, write down the frequency of the sound detected by the listener as the police car, question 6.2.1, approaches the listener. So that first statement, write down the frequency of the sound detected by the listener. What that means is we need to write down the value of FL, because FL is the frequency of the sound detected by the listener. Now they specify two different situations. 6.1, we need to write down the value of FL when the police car approaches the listener. So when it's approaching the listener, that will be this point over here towards 6.2.1. When it is moving away from the listener, that will be this point over here, the away part. That will be 6.2.2. So our question 6.2.1, let us answer that. So we need to write down FL when it is moving towards, and for 6.2.2, FL when it is moving away. So we've already discussed both those answers. When the police car is moving towards the listener, that is the initial point. So our time is 0 then. So that is going to be 170 hertz. Keep in mind the unit of measurement of frequency is hertz, Hz. Okay, next we need to write the frequency of the listener when the police car is moving away from the listener. Because it is moving away, that is going to be the lesser frequency. So that is our frequency of 130 hertz. Okay, now let us move on to the next question. So our next question is question 6.3. Calculate the time, or rather calculate the speed of the police car. Take the speed of sound in air to be 340 meters per second. So that 340 meters per second, which is our speed of sound in air, that is our value of V. Our value of our listener, which we previously mentioned, is 0 meters per second. We now have frequencies for the listener when the police car is moving towards and away. The only thing that we do not have, besides what we are calculating for, is the frequency of the source. we do not have the frequency of the source. So because of that, you'll see that if we were to substitute into our equation and we were to only take into consideration the towards scenario, we would have two unknowns. The first unknown being what we are calculating for, the second unknown being the frequency of the source. Then if we were to say, okay, that's not working out because we can't calculate if we have two unknowns. If we were then to substitute into the equation of moving away, we would substitute all the known values. You would then see that you would still have two unknowns, which is the velocity of the source and the frequency of the source. And another indication that you are meant to use simultaneous equations is because if you look at the structure of this entire question, it's surrounded on two different scenarios. They give you information for two different scenarios. So that is another indication that this is moving in a direction whereby we need to create two different equations, and we need to have one situation whereby we are moving towards, one situation whereby we are moving away, and we will then resolve this using simultaneous equations. A third indication is the mark allocation. This is quite a simple topic, so they won't really give you a lot of marks for a simple question. What I mean by that is if you were given all the values and you were only meant to solve for Vs, which is the velocity of the source, meaning that you were given the frequency of the listener, the frequency of the source, the speed of sound in air, and the speed of the listener. You were given everything that you need. You only had one unknown, which is Vs. It wouldn't be a 6-mark question. Okay. So there's certain indications that can guide you towards what you are supposed to do. So this is question 6.3. I do see that there is a message in the chat, so just give me a moment to have a look at that before we start with our question. Okay, so that has been resolved. Then let us move on. Okay, so we've got question 6.3. Our goal is to now calculate the velocity of our source, meaning the velocity of our police car. So let us make a note of what we have. We need to find Vs, that is what we are looking for. We have VL. We were told that the listener is stationary, meaning that there is a 0 meter per second velocity. We just calculated, we just pulled or extracted the values from the graph for our frequency of our listener in both the towards situation and the away situation. So for now, I'm not going to write those values because they are already there. Let us see, what else do we have? We have the velocity of speed in the velocity of the sound in air, that is 340 meters per second. So let us now start by creating equations. So because we have two different scenarios whereby the police car is moving towards the listener and then away from the listener, I'm going to write two equations and substitute for two different equations as well. So my first equation is going to be towards. That is FL equals V plus VL all over V minus VS. Keep in mind we said that if it is towards, it's plus on top, minus at the bottom. And then my equation for away, that is going to be FL equals V minus VL all over V plus VS times Fs. So keep in mind, if we are moving away, it is minus on top, plus at the bottom. Okay, so someone mentioned, may you please re-explain the velocity part? Okay, so let us go back to our question so that we can explain the velocity part. So there's three different velocities that are in this particular equation or in this particular question. Those three velocities are the velocity of your source, which in this particular case is the police car, the velocity of our listener, which in this particular case is the guy standing on the side of the road, and we have the speed of sound in air that is represented by v, and that is on the numerator and denominator section of our question. Okay, so our first statement states a police car moving at a constant velocity with its siren on passes a stationary listener. If an object is stationary, that means it does not have any velocity, it is still or it is not moving. Therefore, the velocity of that stationary listener, VL, is now going to be 0 meters per second. In addition to that, we are meant to calculate the velocity of the source, which is the velocity of our police car. That is unknown. That is why I've put a question mark. And thirdly, we were told that in question 6.3, calculate the speed of the police car, take the speed of sound in air to be 340 meters per second. So we were now told what the value of V is. The V, which is our speed of sound in air, has a value of 340 meters per second. There was a hand that was up. I believe your name was Philly. Okay, so I see you did post your question. Are we always given the velocity of the sound in air? In most cases, you are told what the velocity of sound in air is, or the speed of sound in air is. We'll have a look as we go through a few more past papers if it's always given, but I believe it is. Okay, so we've discussed our velocities. Okay, let us now start by substituting into our first equation, which is our towards equation. So our first value is FL. Now, if we notice, we've got two FL values, 170 and 130. But I made a note on the diagram that 6.2.1 represents towards. So because we are using the towards equation, we are going to use the value of 170 for our formula. So we substitute 170 equals, we were told that V is 340 plus our velocity of our listener, which is 0, all over 340 minus the velocity of our source. That is the police car. That is what we are trying to calculate. So that is our first equation. We can simplify it a bit if we were to just say 170 equals 340 all over 340 minus Vs. Yeah, all we did was get rid of the plus 0. So I'm going to leave it like that for now. We might come back to it to simplify it a bit more, but let us first look at our away equation and see what we have, so we can then figure out a plan of how we are going to connect both equations. Okay, now in our towards, or rather in our away equation, we have FL. Let us go and see what is the value of FL. So question 6.2.2 answers the question why, or rather what is the velocity of what is the frequency of the listener when the object is moving away. So as you can see, the frequency of the listener when the object, more specifically the police car, is moving away from the listener, that is 130 hertz. So we are now going to substitute 130 equals, we were told that V is 340 minus 0 all over 340 plus Vs times Fs. Now, for the sake of space, what I'm going to do is, instead of having to rewrite this equation, I'm just going to get rid of that plus 0 and that minus 0. So I'll get rid of that as well. Because we know plus 0 minus 0, it means nothing, right? So these are my two equations. I now need to solve for Vs, keeping in mind that I have two unknowns, which is Fs and Vs. Now, because I need to solve for Vs, I'm now going to make Fs the subject of my formula. Okay. If you attended the Newton's second law of motion session, I explained this concept whereby whatever you are calculating for, make the other thing your subject of your formula. Because when you connect both equations, you're going to connect it at the subject, therefore the subject will fall away, and whatever is within the original two equations will be within the simultaneous equation. So the rule is whatever you are calculating for, in this particular case Vs, you're going to make the other variable your subject. Now in this particular case, the other variable is referring to Fs. Now there's a short way that we can do this whereby we divide both sides by what is in the bracket, meaning that in order to get rid of what is in front of our variable Vs, we can divide both sides by what is in front of that, which is the bracket. Now, I understand that might be slightly confusing for certain people, so I'm going to take the longer approach and I'm going to multiply, divide, and simplify as opposed to just dividing by both sides. So I'm going to start off with the towards equation. So this is 170 equals, and I'm going to multiply my Fs with my 340. That is going to give me 340 Fs. From there, it'll be over 340 minus Vs. So from here, what I'm now going to do is I'm going to cross multiply. So this represents one thing. I'm going to multiply that with my 170, and we know that 170 is just over 1. So I'm going to multiply that with the right side. That is then going to give me 170 into 340 minus Vs, which is then equal to 340 Fs. From this point, I need to isolate Fs. I want to get rid of it. So I'm going to divide both sides by 340. That is then going to give me 170 into 340 minus Vs all over 340, which is now equal to Fs. This is now my first equation, my equation 1. All I did was, in order to create my towards equation, I substituted the known values. From that point, I had two unknown values, therefore I solved, or rather I made Fs the subject of my formula. Okay, I'm going to do the exact same thing with the away equation. I've already substituted the known values. The only thing that's left is to make Fs the subject of my formula. So, same thing as before. I'm going to multiply Fs with the 340. That is then going to give me 130 equals 340 Fs all over 340 plus Vs. From there, this is going to be considered one thing. So I'm going to multiply this with 130. I know my 130 is over 1, so I'm going to multiply that with the right side. All I'm doing is a basic cross multiplication. So we then have 130 times 340 plus Vs, which is equal to 340 Fs. From that point, I'm going to divide both sides by 340. That is going to give me 130 into 340 plus Vs all over 340, which is now equal to the frequency of the source. That is now my equation 2. Now you'll see what I mentioned previously, whereby I said whatever you are calculating for, make the other variable the subject of your formula. Because when we connect these two equations, you'll see that we will have Vs as our only unknown. If we were to make Vs the subject of our formulas initially, when we connected them, we'd have Fs in our formula, which is not what we want to calculate for. We need to find the velocity of the source. So it would make, or rather it would simplify things and make our process much faster to solve for the other variable. Therefore, our Vs will be within our equation when we connect both equations. There is a hand up. Dikaledi, you have your hand up. Do you have a question? In order to ask your question, you have to unmute yourself. So you'll see there'll be a line through the mic. Just click on that line and then you can speak up.
I need you to explain more about those formulas. They really differ.
Sorry, I didn't hear you. Please, can you speak up a bit?
I want you to explain more about the difference between these formulas. I didn't really get it.
Oh, the difference between the away and the towards formula.
Yes, please.
Okay. So we've got two different formulas because we have two different scenarios taking place within our question. Now, in the initial question, it is stated that a police car passes a stationary listener. So think of it as you are standing on the side of the road and all of a sudden a police car rushes past you or drives past you. Now, when this police car is driving past you, there's two situations that are taking place. Situation number one is as this police car is moving towards you, you are going to detect a louder sound. Therefore, it is going to have a higher frequency as detected by the listener. The second scenario is when this police car passes you and now starts to move away from you, you are now going to hear a lower or a softer sound. That indicates that the frequency detected by the listener is lower. That is why we have two different equations, because we were told that we needed to calculate the velocity of the police car, and we did not have the value of the frequency of the source, which is the frequency of the police car. Now, due to that fact, we had two unknowns within our equations. If you have a look at the equations, when we initially substituted, you can see that we have two unknowns. So that was our indication that we needed to use simultaneous equations. Now, if we take a step back, why do we have two equations? It's because we have two different scenarios taking place. The first equation represents as the police car is moving towards the stationary individual. The second equation represents as the police car is moving away from the stationary individual. Now, the differences in our equations comes from the signs. If the object is moving towards, it is going to be plus on top, minus at the bottom. If the object is moving away, it is going to be minus on top, plus at the bottom. Okay. An easier way to remember it might be if it's moving towards meaning more, so plus on top. If it's moving away, if you take away from something, you're minusing, so minus on top. Okay. And then the bottom will obviously be the opposite. Does that answer your question, Dikaledi?
Definitely, thank you.
Okay, so for those of you that forgot what is happening, let's just do a quick recap to get everyone back on the same page. So we had a particular situation whereby this police car was passing the stationary listener. Keep in mind that the use of the word stationary implies that this particular person is standing still. This particular person is not moving. Therefore, the velocity of the listener is going to be 0. Okay. Now, from that point, because this police car was passing the listener, there were two situations that were now created. So the two situations that arose were as this police car is moving towards the stationary listener, there is going to be a greater frequency detected by the listener because this police car is moving towards. Then, when this police car passes the stationary listener and moves away from this particular stationary listener, the frequency detected by the stationary listener is going to be lower as opposed to when it was moving towards. That then creates two different formulas. Our first formula is going to be plus on top, minus at the bottom. That is towards. So always keep in mind, whenever the object is moving towards, plus on top, minus at the bottom. Whenever the object is moving away, it's going to be minus on top, plus at the bottom. Okay, that is why we ended up with two different equations, because we had two different scenarios and two different unknowns. Our first unknown is what we were now calculating for, which is Vs. Our second unknown is the frequency of the source. That information was not provided. Okay. Now, I previously mentioned that whenever you are doing simultaneous equations, to make life easier for yourself or to speed up the process, if you are calculating for Vs, make the other variable the subject of your formula. By doing this, when you connect both equations, the unknown that you want to find will be within your simultaneous equation. Okay, so all I'm now going to do is I'm going to connect both equations. So I'm going to connect equation 1 to equation 2. So this is my equation 1 on the left, my equation 2 on the right. Now, in place of equation 1, I'm going to substitute equation 1, which is 170 into 340 minus Vs all over 340. That is then equal to my equation on the right, which is now 130 into 340 plus Vs all over 340. All we have now done is simplify our equations such that Fs becomes the subject of our formula. Once we had Fs as the subject of our formula in both cases, we were now able to connect our equations at the point Fs. And as you can see, the variable that we want to calculate for, which is Vs, remains within our equation. So our only job now is to simplify both equations and solve for the unknown Vs. Now, if you notice, you have 340 as the denominator of both equations. Because 340 is the denominator of both equations, you can get rid of them or you can drop them. The reason being is, if you were to cross multiply this, you'd have 340 on the left, 340 on the right. They would just end up cancelling one another out. It's the same values on both sides. It's the same concept as if you had the same bases on both sides, meaning that if you had 2 to the power x equals 2 to the power 3, you would just drop the bases and leave the exponents. Now, in this particular case, because you have the same denominators on both sides, all we are now going to do is drop the denominators and only write the numerators. Okay, now from there you can see that we have 170 on the left, 130 on the right. We have a few options available to us. We can either multiply those values into the bracket, or we can get rid of the zeros on both sides. Now, what I'm going to do is get rid of the zeros on both sides, because when I multiply into the bracket, it's then going to give me a smaller value, as opposed to keeping the zeros, which will then give me bigger values that I have to work with. So I want to keep my values as small as possible to reduce my chances of error. So on both sides, I'm going to get rid of the zero. You cannot get rid of the 0 within the bracket, nor can you get rid of the 340 within the bracket, because that 340 is connected to the VS's. If it was not addition or subtraction, if it was multiplication within the brackets, meaning 340 times VS, then we could get rid of the VS's, or rather then we could get rid of the 340s on both sides. But because it is plus or minus, that restricts our ability to do so. Now, once we multiply 17 with 340, we end up with 5,780. Once we multiply 17 with VS, we end up with negative 17 VS. From here, we're going to do the exact same thing that we did on the left-hand side, which is multiply the 13 into the bracket. So that is going to give us 13 times 340. That is going to give us a value of 4,420. Now we're going to multiply the 13 into the bracket and multiply it with positive VS. That's going to give us positive 13 VS. Happy, I saw you had your hand up. Do you have a question relating to what's going on?
Sir, why did you cancel out the zeros there?
So I cancelled out the zeros to give myself smaller values to work with. If you were dealing with bigger values, values that have a lot of digits or a lot of zeros, it increases the chances of you making an error. So all I did was I basically just divided by 10. That's just cancelling out on both sides. If I were to leave it...
Okay, sir.
Okay, sure. Okay, so let us continue. So we now have two sets of constants and we have two sets of variables with their coefficients associated. Now, all we're going to do is, just as our normal equations, we move all the variables and their coefficients to the left, and we keep all of the constants to the right. So that is going to be negative 17 VS minus 13 VS. Keep in mind, when you move, you are changing the sign. So that positive 13, when I move it to the left, it becomes negative 13. Now on the right, I have 4,420. When I move 5,780 to the right, that is going to become negative 5,780. Okay. From that point, I can now add up my like terms. So negative 13 minus 17 is going to give us negative 30 VS. From there, I can add up my right-hand side, which is 4,420 minus 5,780. And that is then going to give us negative 1,360. Please allow me a moment to double check this value. 4,420 minus 5,780. Yes, that is in fact 1,360. So from this point, all we now need to do is divide both sides by the coefficient of the variable, which is negative 30. So that will then give us the velocity of this police car as negative 1,360 divided by negative 30. That is then going to give us a value of 45,33 meters per second. So the velocity of this police car as it passes our stationary listener is now calculated as 45.33 meters per second. All we needed to do was create our two different scenarios whereby we had moving towards and moving away. Once we have done that, all we needed to do was substitute those values into our formula, and that would give us our final answer of 45.33 meters per second. If you wanted to simplify your equation in a different way, you could have solved or rather made Vs your subject of your formula, which means Fs would have been within your equation. You would have then had to find the value of Fs, which is the frequency of the source. Once you did that, you would then substitute that frequency of the source into one of the equations in order to find Vs. So there's a few different situations, or rather a few different methods that you could have used. Okay, then Lady, you have your hand up. Do you have a question?
Yes, I do have a question. I wanted to know if this there's other method that you can use beside this one.
When you say besides this one, are you referring to the simultaneous equation way?
Beside the simultaneous method, is there any other method that you can use to get to your answer?
You can use elimination, but
Okay.
elimination is, I believe you did it in grade 10. It's what you did before simultaneous equations, whereby you looked at an equation. Let me just show you an example to remind you. So elimination was the process whereby if you had, let's say, y minus 2x equals 7, and at the bottom you had y minus x equals 14, for example. Now, the process of elimination would be to subtract the top equation minus the bottom equation. So that'll be y minus y plus negative 2x minus x, which would have then, or rather minus negative x, would have resulted in plus x equals 7 minus 14. From here, you would have ended up with negative x equals negative 7, therefore resulting in x as 7. That's a process you might have been able to use for this, but I feel like this might have been slightly more difficult to use because of all the fractions that are involved. But besides these two methods, I don't think there is another method that you could have used, unless another student has an alternative approach that they can think of. But yeah, based on the information that's given and the scenario that's taking place, I believe that this is the only method that you could have used. But yeah, like I said, if there is another student that can think of an alternative approach, you are welcome to speak up and we can attempt it, or you can write it down in the chats. So our next question, we've got a question from 2018. So let us see. And we've got an hour left. So it seems like we are making quite good time today. Okay, so we've got question 6, and you can see we have another big mark question, which is question 6.4. We've got that out of 6 marks. So our first question is Doppler effect. We'll skip that one. So we've got question 6 from a 2018 November exam paper. We've got the alarm of a vehicle parked next to a straight horizontal road goes off, emitting sound with a wavelength of 0.34 meters. Something important to take note of: wavelength, the SI unit of wavelength is always meters. If it is given in something that is not meters, please convert it to meters. If you are given anything else, always convert to meters. Okay, that is in response to wavelength. Next, we have a patrol car is moving at a constant speed on the same road. The driver of the patrol car hears a sound with a frequency of 50 hertz lower than the sound emitted by the alarm. Now that is very important. They've even made it bold for you. So I understand sometimes in an exam you can be rushing and you could just take that frequency as 50 hertz, but that is not 50 hertz. It is 50 hertz lower than the sound emitted by the alarm. So what they're now saying is the driver of the patrol car, which is the listener in this particular case, hears a frequency 50 hertz lower than the source. So let's say, for example, our source is 200. Okay, so for example, if our source is 200 hertz, and this listener now hears a sound that is 50 hertz lower than the sound, or rather than the frequency of the source. It does not mean that the listener is hearing a sound of 50 hertz. When they say lower than, it implies that it is 50 hertz less than the original, meaning that it is 200 minus 50, which gives you 150 hertz. Keep in mind, this is not the actual values of the question of this question that we are doing. This is just an example. Another way of thinking about it is, if you have, or if someone tells you, I am 50 years younger than my grandfather, that does not mean that you are 50 years old. It means that whatever your grandfather's age is, subtract 50 and you will get yours. Now, in this particular case, they state that the frequency of the listener is 50 hertz lower than that of the source, which means that whatever the source is, you subtract 50 and that will give you the frequency of the listener. Okay, so let us move on. Take the speed of sound in air as 340 meters. So the student that asked about this, do they always give it to you? So far, 2 out of 2 cases, we have been given the value of V. So I do believe in most cases, you will be given the frequency, or rather the velocity of the speed of sound in air. So our first question, we've got 6.2. Is the patrol car moving towards or away from the parked vehicle? So we now need to investigate whether this particular patrol car, which keep in mind is our listener, is moving away or towards the parked vehicle. Keep in mind that the parked vehicle is in this case our source, because this parked vehicle is emitting a sound. Let's say, for example, for whatever particular reason this vehicle starts, the alarm starts to go off. Maybe someone tried to break into the car. Maybe another vehicle drove past that particular car too fast. So whatever reason, this stationary parked vehicle is now emitting a sound from its alarm. Now, as this patrol car passes or moves away, we do not know as yet. We don't know what's the situation, whether it's moving towards or away. So whatever is going on, as this patrol car is moving in whatever particular direction, towards or away, it is detecting a frequency 50 hertz lower. So let us go back to what we originally said. We mentioned that if the vehicle, or rather if the object is moving towards, it's going to detect a greater frequency. If the object is moving away, it's going to detect a lesser frequency. So the fact that they have mentioned that the frequency detected by the listener is 50 hertz lower than that of the source. That word lower is important. That word lower indicates that the frequency, or rather that the patrol car is moving away from the source. So if they mentioned 50 hertz greater than or higher than, it would then imply moving towards. But because they've mentioned lower, it then implies that this patrol car, which is now our listener, is moving away from the source. So 6.2 is going to be away. Now they request a reason. Why are we saying that it is away? Or if you were to say towards, whichever you want, whichever you did in the exam, if you said away or towards, whatever option you chose, you now need to give a reason of why you said that. So because we've now stated away, I'm going to state that my reason for stating away is because the frequency detected by the listener is lower. Okay, you can write it out in full. I'm just going to keep it as short form for now. So the reason that we've stated that this patrolman or this patrol vehicle is moving away from our source is based on the fact that the question stated lower than. Now our next question, 6.3. Calculate the frequency of the sound detected, or rather emitted, by the alarm. So keep in mind that this alarm is our source. So we need to calculate the frequency of the sound emitted from the alarm. Now, what is that? That is Fs. We need to find Fs. So before we can find Fs, let us make a note of the known values that we have. So what do we have? We have velocity, or rather the speed of sound in air, as 340 meters per second. We also have lambda, which is the wavelength, as 0.34 meters. What else? We are told that the frequency of the listener is 50 times, or rather 50 hertz lower than the frequency of the source. So we don't have the actual value, we just know it's 50 less. In addition to that, we are now expected to calculate Fs and the velocity of our source, which is the parked vehicle that is emitting a sound, that is 0 meters per second. Well, we told the velocity of our listener. Let us just go back and see. The alarm of the alarm of a vehicle parked next to a straight horizontal road goes off, emitting sound with a wavelength of 0.34 meters. A patrol car is moving at a constant speed on the same road. The driver of the patrol car hears a sound with a frequency of 50 hertz lower than the sound emitted by the alarm. Take the speed of sound in air as 340 meters per second. So we are not given the velocity of the listener. We are just told that this guy moves at a constant velocity, but we are not told what that velocity is. So if you notice, we have two unknowns. If we were to use our VL equals V plus or minus VL over V plus or minus VS times Fs. If we were to use that formula, we would have two unknowns, and we do not, or rather we'd actually have three unknowns, because we don't know what is FL. So FL is unknown, Fs is unknown, and VL is unknown. We have three unknowns, which makes using that formula somewhat more difficult. If we were to substitute Vs minus 50 in place of VL, we would then have two unknowns. What I mean by that is, I'll show you an example of what I mean. So this is our formula. FL equals V plus or minus Vs, or rather VL, all over V plus or minus Vs times Fs. Okay, this is our formula. If we were to substitute 340, Fs minus 50 and 0 into this formula, in place of FL, we know that it is Fs minus 50. Okay, now in place of V, we know that it is 340 that was stated in the question. Our velocity of our listener is unknown. This will still be 340 plus or minus our velocity of our source, that is 0 meters per second, times Fs, that is the frequency of our source. So that is our equation now. And if you look at this equation, we've got one unknown, two unknowns. So we have two unknowns. But the issue is we cannot use simultaneous equations, because we do not have a situation whereby this patrol vehicle is going towards and away. In real life, there is a situation whereby it moves towards and away, but in this particular question, because we are given limited information, We cannot make the assumption, or we cannot go any further and put in our away and towards formulas and then use simultaneous equations. It's not going to work out because we don't have sufficient information. If you remember the previous question, we had sufficient information. We had the away and the towards frequencies, and we were given a whole bunch of other information. But in this particular question, we do not. So we are stuck. Another indication that we are not going to use simultaneous equations is the mark allocation of this question. It's only 3 marks, which means we are not expected to do a lot of work, nor are we expected to use a long method or process. So this equation now does not work. So we can get rid of that. We now need to think of, okay, what other equation can we use in order to calculate the frequency of the source? So we know that because we have lambda, because we have wavelength, we have another option available to us. That is velocity equals frequency times lambda. This is an equation that you were introduced to in grade 10 when you first started physics, and it is an equation that is at the back of your question paper if you want to go have a look. That v represents the velocity of the wave, that f represents the frequency of the wave, and that lambda represents the wavelength of the wave. So in this particular case, the wavelength, or rather the wave that we are associating this formula to, is our sound emitted from this alarm. So this is your scenario in a sense. You have this road and you have this car that is on, or rather parked on the side of this road. Now, this car's alarm is emitting a sound, and that sound is a wave, right? Now, we can use this formula because we have the velocity of that wave, we don't have the frequency of that wave, but we have the wavelength of that particular wave. So we have 2 knowns out of the 3 variables. The only unknown is f. And if you go back to the question, calculate the frequency of the sound emitted by the alarm. That is frequency. We are calculating for frequency. And what value don't we have of that wave? We don't have the frequency. So in this particular question, or in this particular scenario, that f can now be represented by fs. So that is the formula that we are now going to use because we are taking into consideration only one wave. We're not looking at the scenario as a whole, whereby we have relative velocities, 2 different objects moving away or towards one another. That is complicated. We're just restricting our scenario to this one individual parked car. We are only looking at that parked car. We are not looking at anything else. So that v of the wave refers to the speed of sound in air, because keep in mind that is the sound that's being emitted, right? So that means speed of sound in air would represent that v of that particular wave. So we can substitute, in place of v, we'll substitute 340. In place of f, I'm just going to put fs times my wavelength, which is 0.34 meters. Now, from here, all we now need to do is divide both sides by 0.34, and that is going to give us a value. Just give me a second. 340 divided by 0.34, that gives me a value of fs as 1000 hertz exact. There's no decimal. Okay, so I do see that there are a few questions in the chats. Just give me a moment to get to that. If it's 50 hertz higher, then it means you add. Yes, Sandy, if it's 50 hertz higher, that means you plus. If it's 50 hertz lower, that means you'll decrease, you'll subtract, okay? So our next question, which is actually the last question of this particular paper, we've got question 6.4. So question 6.4 states, the patrol car moves a distance of X meters in 10 seconds. Calculate the distance X. So basically what's going on is the patrol car moved past this the stationary vehicle, okay? So in our particular scenario, it started whereby the patrol car moves away from that particular vehicle, the parked car. Now, it then states that the patrol car moves a distance of 10 meters. So let's just put that in a drawing. So this is our source, and let's say we have this patrol car that's moving away. Okay, so this is our patrol car that's moving away. This is our listener. Now let's state, or not let's state, but the question stated that this patrol car moved a distance of X meters away, okay, within a given amount of time. So it's X meters within a given amount of time. Let us go and see what that amount of time is. It's 10 seconds, okay. So this is 10 seconds. So within 10 seconds, this patrol car moved a distance of X meters. We now need to go and find that value of X. What is the distance X meters? Okay. Now, in order to do this, because we have time and because we are dealing with velocities and because we are dealing with distance, that is an indication that we can now use one of our 4 equations of motion. Always keep in mind that certain indicators will tell you what to do. So in this particular case, because we are dealing with velocity, because we are dealing with time, and because we are dealing with distance, we now have the option to use our 4 equations of motion. Okay, so let us start with that. This is question 6.4. Now, let us list our 4 equations of motion so that we can see what variables we have that will allow us to calculate for distance, which is delta x. Okay, so our 4 equations of motion, we have Vf equals Vi plus A delta t. We have Vf squared equals Vi squared plus 2A delta y. We have, what else? We have delta y equals Vi delta t plus 1/2 A delta t squared. And in addition to that, we have delta y. I'm going to replace y with x actually. I forgot we are not doing vertical projectile motion, so it's not vertical displacement, it is horizontal displacement. So we can replace that with x. That is then going to be equal to 1/2 into Vi plus Vf delta t. So these are our 4 equations of motion. Okay, now let us try and investigate which question, or rather which equation we are going to use. So before we even try to guess or try to determine which equation we are going to use, let us take a step back and read our question once more to make sure that we fully understand and remember what is said and what variables we have. So our question states, the alarm of a vehicle parked next to a straight horizontal road goes off, emitting sound with a wavelength of 0.34 meters. A patrol car is moving at a constant speed on the same road. The driver of the patrol car hears a sound with a frequency of 50 hertz lower than the sound emitted by the alarm. Take the speed of sound in air as 340 meters per second. Now that we've read the question once more, there's a statement that now stands out given the question that we are calculating. It's the statement over here. The patrol car is moving at a constant speed. Constant speed implies acceleration is 0. Always remember that. Whenever speed is constant, acceleration is 0. So let us now try to change some of these equations using acceleration as 0. So if acceleration was 0, 0 times delta t, that would disappear. If acceleration was 0 here, that would make that whole part disappear because you multiply by 0 across. If acceleration was 0, it would mean this whole part disappeared because it would be 0. Because remember, anything times 0 is still 0. In our fourth equation, we don't have acceleration, so we don't need to get rid of anything. Now, in our first two equations, it just states that the initial velocity is equal to the final velocity. We already know that because the question stated that the acceleration is 0 based on the fact that velocity was constant. So these first two questions don't help us at all. Now let's have a look at the last two. We need to calculate delta x, so that's good. We have the velocity. Do we have the velocity? Okay, we don't have the velocity of the listener. So that is unknown. And we have time. So if we were to find the velocity of the listener, we would then be able to use this equation. So let us look at the last equation before we conclude and say this is the one we want to use. So if we look at the last equation, we need to find displacement. So that's good. We have initial and final. Actually, we don't have initial and final velocities. Keep in mind that our initial and final velocities are unknown. And because of this particular question, which is the acceleration is 0, based on the fact that the question mentioned the velocity is constant. That means that V initial is going to be equal to V final. So if we were to further continue this last equation, we would have delta x equals 1 over 2 V plus V delta t. We know that V plus V means 2V. So 2V delta t. That then will become a half times 2 becomes V times delta t. So if you notice, the last two equations are exactly the same based on the fact that velocity is constant, meaning acceleration is 0. So we basically only have one equation then to go with, which is just displacement equals velocity times time, because both of them are the same, which then means that we need to first do something before we can actually use this equation, because we do not have velocity, it's unknown, and we are trying to calculate for displacement. So we can't have two unknowns within one equation. And you can see that the mark allocation is 6 marks. So that is another indication that we need to do a bit of work before getting our answer. So we are going to use this formula a bit later. And we now need to find the velocity of our listener. So let us look at what we have. In our previous question, we calculated the frequency of the source. Because we calculated the frequency of the source, we now know what the frequency of the listener is. Because keep in mind that the frequency of the listener was just 50 hertz less than the frequency of the source. So let us calculate that. We calculated the frequency of the source to be 1000 minus 50, which is therefore equal to 950. So our frequency of our listener is 950 hertz. Okay. So we have speed of sound in air, we have VFL, we have FS, we have VS. So our only unknown is now VL. So it is now possible for us to calculate velocity using our equation that we are used to, the whole long equation whereby we have plus or minus. It is now possible to use that equation. So let us start by writing the equation. It is FL equals V plus or minus VL all over V plus or minus VS times FS. Keep in mind that the whole reason that we are using this equation is to calculate the speed of the listener. That is the only reason that we are using this equation. Once we find the speed of the listener or the velocity of the listener, we can then substitute that into the equation we discussed earlier. Displacement equals velocity times time. So let us substitute what is known. We previously calculated that the frequency of the listener is 950 hertz. We were given that velocity or speed of sound in air is 340. Before we proceed, let us now go and identify whether we are going to use plus on top and minus at the bottom, or minus at the bottom and plus, minus on top and plus at the bottom. So always remember that if the object is moving towards, it's plus on top, minus at the bottom. If the object is moving away, it is minus on top, plus at the bottom. So if you look at the frequencies of the listener and the frequencies of the source, you can see that the frequency of the listener is lower than the frequency of the source. That implies away. We were also told that this patrol vehicle detects a frequency 50 hertz lower than the source. So that is another indication that we are moving away. We also previously discussed in question 6.2 that this patrol vehicle is moving away. So let us now go and put a minus on top and a plus at the bottom to indicate that this is moving away. Now our frequency of our velocity of our listener is what we are calculating, and the velocity of our source, keep in mind our source, which is the parked car, is stationary. We then calculated the frequency of our source in question 6.3 as 1000 hertz. So let us substitute that. From there, we now need to simplify. So we have 950 equals 340 minus VL all over 340 times 1000. Now there's a few options that we can take. One option would be to multiply this 1000 into the bracket. The second option would be to divide both sides by 1000. So I'll take the longer method and we will multiply 1000 into the bracket to try and solve for VL. So this 1000 will be multiplied with VL and it will be multiplied with 340. So that is then going to be 950 equals 340 times 1000 minus 1000 VS, or rather VL, all over 340. From here we can cross multiply, so we know this is over 1, multiply with that. 340 will multiply with the 950, so that is going to be 950 times 340 equals 340 times 1000 minus 1000 VL. From here, I'm going to take negative 1000 VL to the left, and I'm going to move all of my constants to the right. That is going to give me 1000 VL equals 340 times 1000 minus 950 times 340. Okay. From here, I'm going to divide both sides by 1000. So that is then going to give me VL as 340 into 1000 minus 950 into 340 all over 1000. The reason that I'm not multiplying these values and putting the answer in my equation is because I don't want to have a very long number that's going to be confusing to work with. It's easier for me to keep it in this form. If you prefer multiplying it and keeping it in that form, you're more than welcome to do that. So all I now need to do is put this into my calculator. So I'll open up a fraction, put 340 times 1000. Make sure that you put 3 zeros. 1000 has 3 zeros, not 2, not 4, 3. Minus 950 times 340, and my denominator is 1000. That then gives me a velocity of 17 meters per second. So the velocity of the patrol car is 17 meters per second. Now keep in mind that we are not done. The whole goal of this was for us to calculate the velocity of the patrol car so that we can substitute that velocity into our displacement equals velocity times time equation. Okay, so let us do just that. So our equation was displacement is equal to velocity times time. We were told that time was 10 seconds. We just calculated velocity to be 17. So we can substitute 17 and 10. And that'll therefore give us, let us not put delta x. We were in the equation that it moves 10 or rather x meters. So let us just keep it as x. We won't put delta x. So x is therefore 170 meters. So our patrol car moved 170 meters within a time frame of 10 seconds. Okay. So the whole goal of this question was for us to calculate the distance that the patrol car moved within 10 seconds. Okay. So in order for us to do this, we listed our 4 equations of motion. We identified which equation we are able to use. Once we identified which question, or rather which equation we are able to use, we then noticed that there were 2 unknowns within that equation. We had an unknown of velocity and we had an unknown of displacement. So that now created an issue. How do we calculate displacement if velocity is also unknown? But we then realized that in the previous question, we calculated the velocity, or rather the frequency of the source. Because we calculated the frequency of the source, that then allowed us to determine the value of the frequency of the listener. So we were then able to use our normal Doppler effect equation to then calculate the velocity of the listener, which was our velocity of our patrol vehicle. Once we calculated the velocity of our patrol vehicle as 17 meters per second, we were then able to substitute that value of 17 meters per second into one of our equations of motion, which was displacement equals velocity times time. And We knew time was 10 seconds, velocity was calculated at 17. Therefore, we were able to get the distance that the patrol vehicle traveled, or the distance that the listener traveled, which was our value of x, as 170 meters. Okay.